screen, and let me apologize because of my handwriting, but I wanted to try this new way of making presentation. So please stop me whenever you don't understand my handwriting. So in this talk, I will be interested in presenting some considerations on the information geometry of Jordan algebra. So I will happily build on a lot of stuff and things that were luckily said in this afternoon. And I will be talking about Fisher-Rao-metric tensor, the Burrell-Ström metric tensor for quantum states, and even there will be some sentences regarding the quadjoint orbit that were just mentioned by Goffredo. So this is work that I am completing now here at the Max Planck Institute for the Mathematics in the Science in Leipzig with Professor Jost and Professor Schwachhofer. So let me just start. Well, before starting, since I fear that you might get bored with my presentation, I will give you a quick resume. So the take-home message of the talk is that if you're interested in the metric aspects of classical information geometry and the metric aspects of quantum information geometry, which are related with the Burrell-Ström metric tensor, then you may look at them as a geometric byproduct of Jordan algebras, of the geometry of the algebraic structure of Jordan algebra. And this is very similar to what happens for Lie algebras and the constant Kirillov-Suryo structure on quadjoint orbits. So let me start. I don't know why it's on page 9. He likes page 9. He likes page 10 and so on and so forth. Okay, now it should work. Very good. So let me start with a brief mention of the classical case. So we are interested in the classical case. I will stick in finite dimensions. So with probability distribution on a discrete space, a finite discrete space, or probability vectors. Now these are just elements of the n simplex, this guy here, which is a convex subset of the space Rn made of probability vectors. So vectors whose components are non-negative and sum up to 1. This guy is not a manifold. It is a manifold with corner because it has a lot of faces. It's a convex set with a nice boundary structure. And so to do proper, well, let me say proper among quotes, differential geometry, what we do usually is to focus, as we already see in Paolo's talk, in the open part, let's say, of the simplex, which is just a set of probability vectors with strictly positive components. Very good. This is an ordinary smooth manifold. It's actually a very nice manifold because it's an open set in an affine space. So topologically is very, very friendly. And the tangent space at a point is just a space of vectors in Rn whose, for which the sum of the components is 0. Now, in this setting, as we saw in Paolo's talk, a very important geometric object is the Fisher-Rao metric tensor, which can be expressed like this, or if you fancy some differential geometric notation, like this: 1 over Pj, dPj tensor dPj. Very good. This tensor, as was mentioned, plays a very important role, especially in estimation theory, because its inverse actually enters the game when estimating the precision of unbiased estimators. Now, in the quantum case, there is, let's say, non-commutative brother of the Fisher-Rao metric tensor, which is the Burrell-Ström metric tensor. But before looking at it, we should see what is the stage, the geometrical stage for the quantum case, because we no longer have probability distributions, we have quantum states. Again, I will stick to finite dimensions. And so we have the so-called space of quantum states of a system, of a quantum system with Hilbert space H. This again is a convex set and is made up of density operators that are just self-adjoint operators which are non-negative, and their trace is equal to 1. Again, this guy here is not a smooth manifold, and unless n is equal to 2, so the simplest case, it's not even a manifold with corner. And as Francesco, with a collaborator, showed some months ago, it is actually a stratified space. So it is still a smooth space in some sense, but its structure is definitely more complex than the simplex. So again, we want to do proper differential geometry and we focus on its interior. So the set of density operators that are also invertible, so strictly positive. This again is a smooth manifold, and just like the open part of the simplex, is an open set in an affine space. So topologically is very friendly.
You have missed the trace equals 1 in the second line.
No, because this guy is already here.
Ah, okay, sorry.
You already have it. But I will comment in a little in very short time on the necessity of this constraint. So we have this tangent space, which is very similar to the tangent space at a point in a simplex. You see, here we have the sum of the components that has to be 0, and here we have the trace that must be 0. So there is some kind of formal parallel between them, even if the actual geometric structures are very different. So I was mentioning the Burrell-Strom metric tensor, which as a non-commutative brother of the Fisher-Rao metric tensor. Now we know from Paolo's talk that this is definitely not the only one. There is an infinite number of them. They are classified in the beautiful work by Petz, and they are in one-to-one correspondence with monotone metric tensor. But this metric tensor here is especially useful when you're interested in estimation theory, because actually it was introduced. This is I'm arguing here. I don't know if this is completely right, but it was introduced in 67 by Elstrom in a paper which is very beautiful. It's a 2-page paper named Minimum Mean Squared Error of Estimates in Quantum Statistics. So he wants to investigate the quantum estimation theory, and he comes up with this metric tensor as the one that gives a quantum Kramer-Rao bound. So this is why I focus on this, because in some sense, if you look at estimation theory, this Burrell-Strom metric tensor is the one you want to use. In fact, it is customary in quantum information geometry to select the metric tensor you're interested in based on the task that you want to perform. Okay, here the expression is this one, where I'm using the inverse of this super operator, which is related, as you can see, with the anti-commutator between operators. Of course, when rho...
Can I ask a question? Why there is A also and B? Where is A coming from, A rho of B? And Ludwig Dabrowski here.
These are just tangent
No,
vectors.
the last line.
The last line here? Yes. Oh, yes, you are definitely right. This is an A. This is an A. Okay. Well, actually, this is a B. Okay. Very good. Thanks. Okay, I wrote them too fast, these slides, I apologize. Okay, so if we have rho and B that commutes, or maybe rho and A that commutes, we see that this expression essentially becomes the Fisher-Rao metric tensor when we understand A and B and rho as diagonal matrices, because they commute and so they can be diagonalized. So in some sense, the Burrell-Strom metric tensor reduces to the Fisher-Rao metric tensor. Now, the question that may pops up to your mind is the following. Can we describe classical and quantum states using the same framework? Because here we use density operator on a Hilbert space, here we use probability vectors, but is there a more general framework in which these objects can be considered as different realization of the same mathematical entity? The answer is yes, and it's given by Jordan algebra. So we will see that essentially classical probability distributions and quantum states may be seen as states on Jordan algebra. So what is a Jordan algebra? It's an algebra. It's a real algebra, so it's a real vector space first of all. Then it is an algebra, meaning that we have a bilinear map, this map here, which is symmetric, so it's abelian. And in general, it is not associative, but it satisfies this other property, which I will not comment. And because we want to be able to deal with probability distributions and quantum states, we need to impose this other condition here. This condition says that essentially the sum of squares, if the sum of squares in a Jordan algebra is 0, then all the squares must be 0, one by one. So in general, a Jordan algebra fulfilling this property is called the formally real Jordan algebra, but in the following, I will focus only on formally real Jordan algebra. So whenever I will say a Jordan algebra, I will actually mean formally real Jordan algebra. Very good. So here we have a Jordan algebra, and we define now a non-normalized state. So what is this guy? It's just an element in the dual, so a linear map from the algebra to R that takes non-negative values when evaluated on squares. Now, squares in a Jordan algebra are essentially called also positive elements. And if you want a very simple, I will not enter into the details, but if you want a motivation for this name, is because for them there is an analog of the spectral theorem, and the spectrum of these objects lies in the open positive half line. So when we define this class of functionals, so what I call non-normalized states, we can immediately see that they are the correct notion we need to deal with classical and quantum states at the same time. So to see this, let's take first the Jordan algebra of bounded measurable functions on your favorite measure space. The Jordan product now is just the pointwise product between functions. And this is an example of associative Jordan algebra, because this product is clearly associative. And now we define what? We define a positive linear function on the algebra just by taking what? An integrable function. Well, it may be like this, such that P the mu of the manifold is of the space is not infinite. Now, if we then define this object, we immediately realize that it is actually a linear functional, and it takes positive values on positive elements. Now, this is almost a probability distribution because I am forgetting about the normalization constraint, right? But from now on, I will definitely forget about the normalization, because to some extent, there is no real need, there is no real reason why we should take 1 as a normalization factor and not 74 divided by pi square. So the normalization feels like something that it's a little bit spurious to the system. So in some sense, it's better to work without normalization until the end and then normalize everything. In fact, some things become clearer in this way. And also there are some models recently investigated, the so-called general probabilistic model, where you want to discard normalization because you want to allow for some missing information, but this is not something I will dwell on. So in this way, we obtain the classical case, the non-normalized classical case, let me say. But we can also obtain the quantum case by selecting the Jordan algebra of self-adjoint operators, where the Jordan product is given by the anti-commutator with this 1/2 factor. And what we do, we take an operator which is non-negative, and again, by means of the trace, we define something that we immediately check to be a linear functional, which is also positive. So it is in this sense that we can speak of the classical and the quantum case together by using Jordan algebras. So now that we are here, we say, okay, Jordan algebras allow to speak of classical and quantum states using the same object, but this is just, you know, some algebraic statement.
Can I ask again one other question?
Of course.
So your functionals are actually also functionals on the usual C-star algebra.
Yes.
Built. So why you chose Jordan at this point rather than the full all bounded operators and, for instance, all complex valued functions?
Because I will use only the Jordan product.
Okay.
So it is true what you say. It's true. From this type of Jordan algebras, we can construct also, we can look at them as the self-adjoint part of a bigger sister algebra. That is true. Now, the converse is not always true, but it's not only this the reason I am focusing on Jordan algebras. The reason I am focusing on them is because we will use only the Jordan product. In a sister algebra, you would have an associative product, an involution. These are extra structures that, for the purpose of this talk, are not needed. Of course, if you have them, then you can add something else.
Okay, thanks.
Okay, so the question is, we have this Jordan structure and we are able to essentially define classical and quantum states, but can the Jordan product say something about the geometry of classical and quantum states? So can it say something on the Fisher-Rao metric tensor and on the Burel-Strom metric tensor? Of course, since I am giving this talk, the answer of this question is yes, they can say something. And how can the Jordan structure, so an algebraic structure, tell us something on geometrical object? Well, this is something that is well known in the theory of Poisson manifolds, because if you have a prototype of Poisson manifold is the dual of a Lie algebra. And in fact, the Poisson tensor on the dual of a Lie algebra is determined by the Lie algebra structure. How? In the way that we just apply to the Jordan algebra case, because it actually works for any type of algebra. So just to be clear, we take J to be a Jordan algebra, but in principle, J can be any algebra. We take a basis on it, and we define the structure constants of the product in this base. So this gives us these coefficients here. Of course, if your algebra is a Jordan algebra, you will have that djkl is equal to d of kjl because of the symmetry of the Jordan algebra. If your algebra is a Lie algebra, you get a minus sign and so on and so forth. But in principle, you don't need these structure constants to be related to a Jordan algebra or a Lie algebra. But anyway, you have these constants, and then what you do? You build this contravariant tensor on the dual space. So you take the Cartesian coordinate system on the dual space, which is associated with this choice of basis. And then you just write down this formula here. So I know it's not a very sophisticated way to introduce a tensor field, but it works. And you can also frame it in a more fancy way, but it's very not useful for the purpose of this talk. So this is a contravariant tensor of type 2, which is symmetric because the Jordan product is abelian. So this is almost like the inverse of a pseudo-Riemannian tensor. We don't know anything about its signature. What we know is just that it's symmetric. So it feels like the inverse of a pseudo-Riemannian tensor, but unfortunately, you cannot invert this tensor. So it is not the inverse. And in fact, its rank changes on the whole dual of the space. This also happens in the Lie algebra case. So this tensor R fills the Jordan product because actually it's defined in terms of it, but it's not invertible. So it's not quite the object that we want because we are looking at metric tensor, but it is not invertible on the full dual space. But remember that we are interested only in states, so non-normalized states. These are not arbitrary linear functionals. They must be positive. So it's not on the whole space that we should worry to invert, let's say, this tensor here. we may look at submanifolds of J star that are made of positive linear functionals on which this tensor is invertible. And this is precisely what you do when you have a Lie algebra, and the result are just the coadjoint orbits that Goffredo were mentioning before. So you in the Lie algebra case, this guy is associated with the Lie product, and what you do is to find submanifolds on which the tensor is invertible, and you discover that these manifolds are symplectic, and the symplectic form on these manifolds is precisely the inverse of this tensor. And we will do precisely the same thing, but for a Jordan algebra. So if you already know the theory of coadjoint orbits, the rest of the talk will be essentially trivial. But if you don't worry, because I will never rely on it. I will try to be as simple as possible, but of course, please ask any question you might have. So to actually look at these manifolds, we first of all look at what? At a distribution on the tangent space that the Jordan tensor defines. Of course, I forgot to tell you that I will refer to this tensor R as the Jordan tensor for obvious reasons. Now, this is just at each point psi in J star, it's just a subset of the tangent space, which is made up of all those vectors, which can be defined as the contraction of the Jordan tensor with any one form on J star, and then evaluated at the point psi. At each point, this is a subspace of the tangent space, and the collection of these subspaces is what is known as a distribution, and we call it Jordan distribution for obvious reasons. Now, what we want is to find integral manifold for this distribution, which means submanifolds in J star, such that their tangent space is precisely the distribution at the point psi. Now, integral manifolds need not exist in general. Now, for a Lie algebra, so when our tensor is associated with the Lie algebra, it turns out that they always exist, while for Jordan algebras, they in general don't exist always, but we will see that they exist precisely whenever we like them to exist. So in the following part of the talk, I will try to build this type of manifolds. How? Well, I want to be guided by the Lie algebra case. And so what I will do is try to look at them as orbits of a suitable group. How? Well, first of all, J star is a vector space. So every element in the distribution at psi is actually the image, well, the evaluation at the point of a linear vector field. This is essentially because here, the one form that we need are actually enough like this. So we just need this type of one form to generate actually the whole cotangent space at each point. So we only need this type of one forms to define the Jordan distribution. So we have this type of vector fields, which you can read immediately here. This formula follows immediately from this expression of the Jordan tensor and this expression for the generating one forms. These are clearly linear vector fields, and they generate the distribution. This is nice because linear vector fields are very friendly vector fields. In fact, they are in one-to-one correspondence with linear map on the space. How? Well, like this. You take your favorite linear map, you write it like this, where this is a basis in your vector space, and then you define a vector field simply like this. Now, in our case, the generating vector fields are linear vector fields associated with these maps here, which in turns are dual map of maps on the Jordan algebra. Because remember, our background is the dual space of a Jordan algebra. So there are linear maps on this dual space, which are the dual of linear map on J. In particular, we consider the left multiplication maps, which are maps of this type. And the generating vector fields are precisely the linear vector fields associated with what? With the dual maps of the left multiplication, when A varies, of course, in the whole Jordan algebra. Another interesting property of linear vector fields is that their commutator is easily computed because it's just the linear vector field that we associate to the commutator of the linear maps seen as matrices, let's say. Why is this instance relevant for us? Because it's part of the structural theory of Jordan algebras that the commutator between the left, one moment, the computer is without, I need to charge it. Well, okay. So it's an important result that the commutator between the left multiplication maps in a Jordan algebra is a derivation of the Jordan product. And derivations are a Lie algebra. They form a Lie algebra, which is the Lie algebra of the group of automorphism of the Jordan algebra. But the point is that this instance allows us to build immediately a Lie algebra for our Jordan algebra. This is just the direct sum of what? Of the vector space made up of maps that are of the form L of A, so the left multiplication maps, and the linear span of their commutators, which are derivations. So this you can prove is a Lie algebra, which is canonically associated with your Jordan algebra. And because of this formula, and because the generating vector field of the Jordan distribution are the linear vector field associated with the dual of these left multiplication maps, what we can conclude is that, well, upon showing that the commutator between dual maps gets a minus sign, we can show that the algebra, that the generating vector fields, they really close on a Lie algebra. This is wrong. So this is the linear vector field associated with this map. So what we find with the minus, what we find out is that the generating vector fields, they don't close a Lie algebra by themselves, but there is always a Lie algebra, as small as the smallest Lie algebra containing them, which is precisely this Lie algebra here, which is canonically associated with every Jordan algebra, and it's called the structured Jordan algebra or something similar. Now, why is all this relevant with respect to integral manifold? Well, because linear vector fields are always complete. So the Lie algebra spanned by the generating vector fields and their commutator is always the Lie algebra representation of a group action. In this case, its group is a structural group of Jordan algebra. And it happens, so we have the orbits of this group action. And it turns out what? That the distribution of the Lie algebra, so the tangent space of the orbit, is generated by the Jordan distribution by essentially definition. So when we want, if we want M to be an integral manifold, the only condition that we have to really care about is to be sure that the Jordan decomposition, so the canonical decomposition at the point xi, coincide with the distribution of what? Of the representation of the structure algebra. If this is the case, then our distribution is integrable at that point, and we may obtain an integral manifolds. Integral manifolds that, because of these chains of equality, because this becomes an equality in the integral manifold case, will be essentially an open subset of the orbit. So what this is telling us is that we have hope to find integral manifolds. We have to do what? We have to study orbit of this group action and analyze and check for this condition. Of course, in general, this is not an easy task, but in specific examples, you can do it. But why is all this relevant? Because let's fix M to be an integral manifold so that we have this chain of equalities. what happens then? We can define on this tangent space a bilinear form, which is the one I'm writing here, which, remember, this is the tangent vector associated with the generating vector fields YA. This is the tangent vector at Xi associated with the generating vector field Y of B. And the bilinear form on them is just this form here. Now, if you are in the Lie algebra case, this will become something like AB, where this is the Lie bracket. And it is precisely the constant Kirillov-Suryo symplectic form on the coadjoint orbit. But so since the Lie product is antisymmetric, it will become, in fact, an antisymmetric covariant tensor. That's why it's a symplectic form. But for the Jordan case, the product is symmetric. So this tensor is actually symmetric. On the integral manifold, it is also invertible because of these chains of implications. What does it mean? It means that on the integral manifold, we obtain at each tangent space a bilinear symmetric form which is non-degenerate. Now, the association of a bilinear form to every point in our integral manifold, it can be shown that it's smooth, and thus what we obtain is a pseudo-Riemannian metric tensor on this integral manifold. I say pseudo-Riemannian because we don't know anything about the signature of this guy, but it's already clear that if Xi is a positive element in our Jordan algebra, then we immediately obtain what? That the norm of any tangent vector is just Xi evaluated on a positive element, which will be greater or equal than 0. It will be 0 only when A is associated with the 0 tangent vector. So this is actually a Riemannian metric tensor. So it turns out that really the Jordan algebra structure contains information on the geometrical quantities, which is a Riemannian metric tensor. Of course, we now have to check if everything works fine in the cases we are interested in. So we have to check who this tensor is in the classical and the quantum case. So I will now essentially give you these two examples, and then I will conclude my talk. So the first case, the classical case, we take as Jordan algebra the real number Rn with component-wise multiplication. Again, this is an example of associative Jordan algebra. The Jordan tensor in this case is simply this one. And you can, I think you can immediately see that this guy contains the Fisher-Rao metric tensor, which is essentially its inverse. But we have to get rid of all the points in which xj is equal to 0. But let's perform our procedure. So we compute, first of all, what? The generating vector fields, which are like this. And we immediately realize that they commute. So if we take two arbitrary generating vector fields, their commutator will be 0. So in this case, they close a Lie algebra, which is an abelian one. And actually, the structure algebra collapses into just this set. So in this classical case, we always have this condition fulfilled. So all orbits of this group will be integral manifolds for the Jordan tensor, and the Jordan tensor will have, and there will always be given a point, an integral manifold of R passing through that point. So who are these integral manifolds? Who are these orbits? Well, it turns out that they are not so difficult to characterize, because if I take my linear functional, then it's transformed, so its orbit is given by all those linear functional. There are just the linear functional as before, for which every component is multiplied by strictly positive elements. So I can essentially dilate all the components to my complete desire, but I can never add zeros. So if my linear functional has 3, let's say, non-zero components, then the orbit, all elements in the orbit will have 3 non-zero components, which is actually something nice because it allows you to show that the open part of the simplex is actually an orbit of this group action. So the manifold that we are interested in the classical case turns out to be precisely the maximal orbit of this group action. And again, by doing the computation, like it's just really a matter of reproducing, of performing trivial computation, what we obtain is that on this manifold, which is also an orbit, the metric tensor that we obtain is this one, which, when we recall how our vector fields are written, implies that the metric tensor that we have is this one, which, if you remember the second slide I wrote, is precisely the Fisher-Rao metric tensor. But what is more is that you can actually not focus only on, remember, the simplex, the whole simplex is a manifold with corners. So we have the open part, which is this one, but we have also faces. And it turns out that the faces are just g-orbits themselves. So faces of the simplex are orbits. And on each of these faces, we obtain a similar tensor.
Dario, you have 4 minutes.
Yes, I will make it. And on these faces, the result that you have is that the tensor that you that the Jordan product allows you to define is precisely the Fisher-Rao metric tensor on that face. So the Jordan product has information on the metric tensor on all the boundary of the, on all the smooth part of the boundary of the simplex. Now the last case is the quantum one, where we have the Jordan algebra of self-adjoint operators. Of course, we are in finite dimension. Otherwise, there is a lot of technical. There are a lot of technical difficulties. Again, we know that our functional are associated to operators through the trace. What happens here? If we compute the commutator between the left multiplication map, what we obtain is something that is associated with the commutator. Well, it's not precisely the commutator because it has this factor 1/2 times I between operators. And this, to connect with the question that was asked in the beginning, is this part, the fact that this commutator is precisely related with this commutator part, is telling you that it's not only a Jordan algebra, but it's the Jordan algebra, which is the self-adjoint part of the C-star algebra, because this is telling us something on the non-commutative structure that you before were not able to see because we were in the classical case where everything was commutative. But anyway, you perform everything that you have to perform and you obtain what? That the structure algebra is just the algebra of left multiplication, isomorphic to the algebra of left multiplication map plus the special unitary group. Now, an element so the group that you obtain is just the group of general invertible linear operator on H. So this is an element, and the orbits are this one. Now you see that this action preserves positivity, and if psi tilde is strictly positive, so it's invertible, then also the elements in the orbits will be invertible. And actually, all invertible positive operators are in the orbit. So positive operators, invertible, are an orbit again. This orbit is open in the dual space. So what does it mean? Well, it means that its dimension is maximal. So we just have to check what? We just have to check that to be sure that it's an integral manifold. We just note that what? An element in the canonical distribution is written like this, which means that it's the image by means of the left multiplication map between associated with psi tilde of an element in the Jordan algebra. But since psi tilde is invertible, Also, the left multiplication map is invertible, so its image is the full Jordan algebra. And since we just have to take the dual, but the dual in finite dimension has the same dimension as the original space, we conclude that the Jordan distribution is integrable at all points in these orbits of invertible operators. So this is an integral manifold of the Jordan distribution. And if you do all the computation, I'm sorry, I'm really speeding up now, but if you do it, what you obtain is what is the Bure-Elstrom metric tensor, but now it seems in disguise because you are evaluating it on the tangent vectors that you obtain through the generating vector fields, which are not the usual tangent vector that people use in quantum information geometry. But if you use them, then the explicit phase of the Bure-Elstrom metric tensor becomes this one, which is definitely simpler than the one involving the inverse of this superoperator. And that's essentially finishes my presentation. So just to conclude, we have seen, and I hope I convinced you, that the Jordan algebra structure is enough to encode for the geometrical properties of the Fisher-Rao metric tensor and of the Bure-Elstrom metric tensor. Thank you.
Sorry, I was muted. Thank you. Thank you, Florio.